This is Algebra 2, Lesson 7-2, Properties of Exponential Functions. You can apply 4 types of transformations that can change the graph of an exponential function. You can apply a stretch. The factor a in y equals a times b to the x can reflect the graph of an exponential function when the absolute value of a is greater than 1. Okay? So that will stretch it, it'll also reflect it. You can compress it, which is the factor a in y equals a times b to the x can compress the graph of an exponential function when the absolute value of a is between 0 and 1. Okay? A reflection is the factor a in y equals a times b to the x can reflect the graph of an exponential function in the x-axis when a is less than 0. You can transform it. Okay? It will translate it horizontally by h and vertically by k when you have the equation y equals a times b to the x minus h plus k. As you can clearly see that x minus h and k keeps coming up over and over and over again because that's the general form of an equation. So if we have graphing something y equals a times b to the x, how do the graphs of y equals negative 0.5 times 5 to the x compare to the graph of the parent function? Now to do this, we should make a table with both the parent function and the new function in it so that we can graph them both on the same set of x and y axes and then see how they change. And then we'll compare that to the equation so that we don't always have to graph them to be able to describe what happens to them. So let's take a look at this first equation. We have y equals a times b to the x. The parent function is y equals 5x, 5 to the x power. So if it's negative 2, that's going to be 5 to the negative second power, which is 1/25. 5 to the negative first power is going to be 1/5. 5 to the 0 power is going to be 1, and 5 to the first power is going to be 5. Okay? If we multiply 5 to the x power by negative 0.5, okay, in other words, you're going to multiply it, you're dividing it by 2, you're basically dividing it by negative 2. 1/25 becomes negative 1/100. Okay, because if I multiply 0.5 times, or a half, excuse me, I'm multiplying 25 by 0.5, I get negative 1/100. If I multiply 5 by 0.5, I'm going to get negative 1/10. If I multiply 1 by 0.5, I get negative 1/2. If I multiply 5 by negative 0.5, I get negative 2.5. So if I was to graph this first function, obviously graphing negative 1/100 is going to be a little difficult. So I'm probably going to skip that one, or at least not have it to be as close as I wanted. Okay. All right. Now I'm just going to graph this one smack in the middle here. Okay. So I have my x and y axes. X here, y here. If I graph these, graphing negative 2, negative 1/100 basically means it's pretty much on the green line, even though I really don't want it to be. Oops, negative 1/100 is below the green line. Silly me. Actually, let's graph the parent function first. Okay, so I'm going to undo that. I should graph my parent function. I'm going to graph my parent function in purple, and I'll graph my new function in red. Okay? So negative 2 1/25. Negative 2 1/25 is basically on the line. And then negative 1 1/5 is barely off my line. And then 0 1. Okay, 0 1. And then 1 5. 1 2 4 5. So my apparent function looks something like this. Y equals 5 to the x. Okay. My new function, my y equals negative 0.5 times 5 to the x, I will have negative 2, negative 1/100. So it's going to be really, really close to the line there. I'm going to have negative 1, negative 1/10. It's still really close to the line. I'm going to have 0, negative 1/2, which is right here. And then I'm going to have 1, negative 2.5, which is right here. So if you can, as you clearly see, it's actually decreasing even more rapidly than it was increasing. Okay, so this is going to be y equals negative 0.5 times 5 to the x power. Okay, so let's compare our graphs here. If we were to compare our graphs, it's reflected over the x-axis. We see that. Okay, the negative 0.5 reflects it over the x-axis. Okay. reflects the graph of the parent function over the x-axis. That's the first thing we should notice. Right. Okay. It compresses it. As you notice, now it's going down even more rapidly than it was before. Okay. So it compresses it by a factor of 0.5. And if we look at this, the domain, it's still all real numbers, isn't it? It doesn't matter what I put in for x, I can still put in any number I want for x, so the domain remains unchanged. So the domain doesn't change. The range becomes y is less than 0. Right? Notice here in my blue graph here, off to the right here, my blue graph never gets higher than 0, so my range is y is less than 0. Okay, and my y-intercept now is 0, negative 0.5. So it still becomes 0a. Okay, so it's reflected, it's compressed. The domain doesn't change, the range does change from being y is greater than 0 to being y is less than 0, and the y-intercept stays at 0 and a. Okay. All right. Now, a horizontal shift y equals a times b to the parentheses x minus h power is the same as the vertical stretch of compression of y equals a times b to the negative h times b dx. It's kind of a weird way of writing the equation. The vertical shift y equals a times b dx plus k also shifts the horizontal asymptote from y equals 0 to y equals k. So if you have a vertical shift, it will shift your asymptote as well. The same number of units that you shift your graph, your asymptote will shift that many units. So if your shift is vertically up 2, your new asymptote then is going to be y equals 2 rather than y equals 0. So let's take a look at this. How does the graph of each function compare to the graph of the parent function? In this first one, we have y equals 4 to the x plus 2. So let's make a table of values for my parent function. Y equals 4 to the x. Okay. If I have 4 to the negative 4th, that becomes, okay, 4 to the negative 4th becomes 1 over 256. That becomes 1 over 4 to the 4th. 4 to the negative 3rd becomes 164. 4 to the negative 2nd becomes 116. 4 to the 0 becomes 1. 4 to the 1st is 4, and 4 squared is 16. So that graph is graphed right here in the black. And that happens to be y equals 4 to the x. We'll just label that one nicely. So if I'm going to translate this, x plus 2 happens to be a horizontal shift, 2 units left. Okay? The y equals 4 to the x plus 2. This is shifting it left 2 units. There's no up or down. Yeah. So what I could do is I could say, instead of this being 4 to the negative 4th, it's now 4 to the negative 2nd, so it becomes 116. So instead of being negative 4, 256, it's negative 4, 116. The easiest way to do it is just pick points and move them 2 points to the left. And so if I chose this point right here and I moved it 2 units left, I'll do it red, it would go there. This 2 units left, 1, 2 would go here. This 1, 2 units left, 1, 2 would go there. They keep those 2 graphs getting points, but you don't want them. Right here, 2 units left would go here. This 1, 2 units left is going to go there. This 1, 2 units left. Right. So you're getting the point here that it looks something like this now. So there's my graph of y equals 4 to the x plus 2. So the same transformations apply to exponential graphs as they've applied to every other graph that we've dealt with this year. So without graphing, let's take a look at y equals 5 times 0.25x plus 5, and let's compare that to the parent function. Okay. The parent function would be, okay, just in case you didn't know, the parent function of this would be y equals 0.25 to the x power. Okay, that would be the parent function. Okay. So what did they do? They multiplied it by 5. Okay. So we stretched the graph of y equals 0.25 of x by a factor of 5. Because that's what the a term is. Okay. Now we translated the graph. And you notice this 5 here translates the graph up 5 units. Okay. So we can now look at a graph and tell what it's going to do by just looking at the equation, and we can also graph the graph once it has been changed. Okay, so basically, the parent function is y equals b to the x. You're going to stretch it if the absolute value of a is greater than 1. Okay, in other words, because remember, if it's negative, it reflects it. That's why they're saying the absolute value of a versus just a. So if the absolute value of a is greater than 1, like the last one was 5, it's going to stretch your graph. It'll shrink your graph if the absolute value of a is between 0 and 1, a fraction or a decimal, like 0.5. It will reflect it across the x-axis if a is less than 0. And it translates it horizontally by h and vertically by k. So all the transformations combined give us this equation right here, y equals a times b to the x minus h power plus k. How do we apply this? Well, we can actually apply it. Okay, let's take a look at something with coffee. I'm not a coffee person, so I really care less how fast coffee cools. But some people really do want to know this. The best temperature to brew coffee is between 195 and 205 degrees Fahrenheit. Lower than that, you don't extract as much flavor from the beans. Higher than that, you burn the beans. Coffee is cool enough to drink at 185 degrees Fahrenheit. That's still hot, but some people like their coffee really hot. The table below here shows the temperature readings from a sample cup of coffee. How long does it take for the coffee to reach a temperature of 100 degrees Fahrenheit? Okay, so the first thing we're going to do here is we are going to look at our table. At 0 minutes, it's 203 degrees. At 5 minutes, it's 177. At 10 minutes, it's 153, and so on. So we're going to plot the data on a graphing calculator to determine if an exponential model is realistic. If you've got the Inspire, you're going to use the spreadsheet model. Okay, you're going to go to Add List of Spreadsheets, okay, and you can either use X and Y. I'm going to use time and temperature just because it's easy. Okay, so time for my X and temperature for my Y, just as I like that. You don't have to. You can use X and Y if you prefer. And I'm just going to put them in there. For your 84, just use list 1 and list 2. Okay, so I have 0, 5, 10, 15, 20, 25, and 30. And temperature, put in 203, 177, 153, 137, 121, 111, 104. You should be doing these with me on your calculator because I already know how to do these. You probably don't, and this is going to be a little bit different than what you're used to. Okay, so once I have that in there, remember on the Inspire, then we're going to go to Add a Page, and we're going to do data and statistics, and we're going to get those 20, and we're going to drag, put the X variable in the Y variable. So I want time was my X value, and temperature was my Y value. And if I look at it, I get a nice little graph that looks something like this. This is my X and Y axis. I get dot separate like this, which means it does look like it fits an exponential model. So the exponential model is realistic. Okay. Now, a graphing calculator will assume that the asymptote is y equals 0, unless you tell it something else. With coffee, you do have to realize any hot beverage cannot cool down further than the room temperature. Once it hits room temperature, it can't get any colder than room temperature unless you put it on ice. So if you're just sitting something in the room, it can never get below room temperature. So since room temperature is about 68 degrees Fahrenheit, we're going to subtract 68 from each temperature value. Okay? So you can do that by making a third list. And the easiest way to do that, right, is on the Inspire. Go back to your list and spreadsheets. Remember, if you do the control and up arrow, you can go back to that lovely list that you made. Okay, so I'm going to go back to my lovely list. And in C, I'm going to put, for C, I'm just going to put T instead of temperature. Okay, and then right underneath that, you have that equal bar before you get into the 1, 2, 3, 4, 5. There's, I'm going to put an equation here, and I'm going to put it into okay, I'm going to put in time minus 68. So T is going to equal time minus 68. Okay. Excuse me, it should have been temperature minus 68. I messed that up. So go back up there and put temperature minus 68. So temp, T-E-M-P, minus 68. If you do that, okay, you're going to get these new temperatures of 135, 109, 85, 69, okay, 53, 43, 36. Okay. So now we want to, if you're using the Inspire, or the 83, you're just going to do let L3 equal L2 minus 68. Okay, what it says there. So using your data, L1 and L3, or for us, time and T, okay, let's find the exponential model. So I'm going to add a page, calculator, I want statistics, but this time I want exponential regression, so it's under stat calculations. Pick up exponential regression, EXPREG. My X list here is going to be my time. My Y list on mine is going to be T. My temperature, that's my T. Okay. I believe it's T. I'll find out really fast. Okay. And I'm going to get 134.516982526 times 9.560 times to the x power. So I get an equation that looks like this. Y equals 134.52, I'm going to round it to that. 134.52 times 0.956 to the x power. Okay. Now we have to translate that vertically 68 units to model the original data. Okay. So our new equation is going to be y equals 134.52 times 0.956 to the x power plus 68, because we have to put that 68 back in there. Okay, so we need to model the original data. Now, we're going to use this model to find how long it takes coffee to reach a temperature of 100 degrees Fahrenheit. Okay, so once I put this in my graph, okay, so I'm going to graph this. I'm going to graph just that equation, the one that I actually truncated it, made it shorter, just because it's going to fit in nicely. So I'm going to put a graph here, and I'm going to put in my graph y equals 134.52 times 0.956 to the x power plus 68. It may or may not show up on my graph. I really don't care. I can change my window if I wanted it to show up on the graph. But I really want my table. So I'm going to pull up my table at this point in time. And I want to know, okay, how long it takes for my coffee to reach a temperature of 100 degrees Fahrenheit. Okay. If I look at this, we know it's going to be over 30 minutes, because if you look at your original table way up here, it's going to be more than 30 minutes. So probably 30 point something because it's really close. So I'm going to change my window setting on my table. So hit your menu, go to your table, and do your edit table settings. Okay, I'm going to let my table start at 30, but I don't want it to go by whole units. I want it to go by tenths, so I'm going to put 0.1 in there. Okay, hit OK. Okay, and then if I look at this, now I have at 30.1 minutes, it's 102 degrees, 0.79. Okay, so let's see here. I'm getting down. So at 30.7 minutes, okay, it's at 101.794. At 30.8 minutes, it is at 101.642. Okay, 30.9 minutes, I have 101.491. At 40 minutes, why did I go over here? 30. I know it's over 30, so let's, so I've got these numbers, it's still way over 101, so let's scroll down. At 31.7, so at 31.7 minutes, I have 100.307. Okay, so it's really close to 100 degrees. 3.8, 31.8, excuse me. I have 100.162 degrees. At 30.9, 31.9, I have 100 degrees, 0.017. That's almost exactly 100 degrees. And if I go to 32 degrees exactly, I have 99.87. So basically, it's going to be, how long is it going to take to reach a temperature of about 100 degrees Fahrenheit? Around 31.9 minutes. Okay? It will take about 31.9 minutes to reach a temperature of 100 degrees Fahrenheit. Okay, so that's application of an exponential model. Okay, now, up until this point, we've worked with rational bases, rational numbers. Okay, no, not just little decimals that don't terminate like pi or a square root. However, exponential functions can have irrational bases as well. One important irrational base is the number e. Believe it or not, there is a number e on your calculator that happens to be a number, not a variable. Natural base exponential functions are exponential functions with a base called base e. It's called a natural function or a natural log. These functions are useful for describing continuous growth or decay. The exponential functions with base e have the same properties as other exponential functions. And basically what we do is, here I have the number e. At the left here I have this lovely little graph, which is the function y equals 1 plus 1 over x to the x power. One of the graph's asymptotes is y equals e, where e is an irrational number. If you plugged e into your calculator, and you just pulled it up, okay? If I put E, remember the pi key on your Inspire that has a little arrow, if you hit that pi key, if you move over a couple times, you'll see E. If you put in E, it's just going to give you an E, but if you hit Control Enter, it's going to change it to a decimal. And you'll notice it's approximately equal to 2.718281, blah, 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 blah. Yeah, there is an E key on the 84. You just have to find the E key, and it's, if you look for the E key, E is right above your division sign. So you hit the second E and then hit the division sign and you hit E. Okay? So, how is E helpful? So, there are 3 ways we can evaluate E. Really easy, mediumly easy, and ridiculously stupid, in my opinion. My opinion only. Please don't take that for the possible truth. The easiest way is to use the E to the X key on your calculator. Just use the E key. If you need E to the second power, and in this case, we're going to evaluate E to the second power. So all I'm going to do is on my calculator, I'm going to pull up E, okay, whether you have the Inspire or the 84, hit E, square it, okay, and make sure you change it to a decimal. So E squared is approximately equal to 7.39, 7.389,056, etc., etc., etc. Whichever calculator. You can graph E to the X. Okay, and when you graph E to the X, you just basically put in E to the X on your calculator. It puts you a nice little graph. And then you have to try to figure out where exactly E squared is. So you have to find out what happens when X is 2. So if I graph this, this is not my favorite way by any stretch of the imagination. And because to me, it's really annoying because you have to trace over your graph. If I put in my function e to the, okay, e to the x power, e to the x power, that's what you put in the calculator, you're going to get a graph that looks similar to this, and then you're going to figure out where 2 is, and you're going to have it intersect. Okay, so you're going to go up your graph, and you're going to have it intersect where 2 is, and you're going to try to read that off your graph, or you're going to try to get your graph to read it for you. Okay. The other way to do is use a table of values. So you can go to your table once you have that graph. Do realize that the table has a tendency to round a little faster. The table is actually, of all of those, this is the annoying way. Because you have to read it off the graph. Okay? This is okay because you've got a table, and your table is going to truncate your e value. It's going to put it to 4 or 5 decimals, depending on however you put it. Okay? But at least you can go down to where x equals 2 and read that off your graph. It's going to be about 7.38905. So the easiest way is just to use the e to the x key on your calculator. But there are 3 methods. Now I've shown them to you. This is the best method. Okay. This is the second best method. This is a nice visual. Okay. It's a nice visual, but it doesn't really help you find it because trying to trace it until you get to where x equals 2 is a bit annoying. Okay. Now, in lesson 7.1, we studied that interest was compounded annually. Okay? Not always is interest compounded annually. For me, my savings account is compounded quarterly, once every 3 months, 4 times a year. The formula for continuously compounded interest, otherwise known as credit cards, uses the number E, which is why people can never figure out how much interest they're paying on their credit cards because unless they know how to use E, they're not really sure how to figure out their interest. Continuously compounded interest is found by the formula A, capital A, which is the amount of your money in your account, equals capital P, which is your principal, the amount you originally invested, or the amount you originally borrowed if it's a loan, times E, which is the natural number E, to the R power, that's your annual rate of interest as a decimal, and T is time years. So let's take a look at a continuously compounded interest formula. Suppose you invest $1,050 at an annual interest rate of 5.5% and compound it continuously. How much money will you have in your account after 5 years? Okay. So the formula is A equals P e to the RT. And we're looking for A. P is my principal, which happens to be $1,050. R is my interest rate, which is 5.5%. As a decimal, that's 0.055. Okay? And time is in years, and that's 5 years. So if I was to plug this into my formula, I'm going to have A equals $1,050. That's my principal, times E to the 0.055 times 5 power. Okay? So if I put all that on my calculator, just make sure that when you put it in your calculator, you make sure that the power stays up there. So 1,050, find my E key, E to the 0.055 times 5. Okay? And if you do that, you should get $1,382.36. Really round linear to cents. $1,382.36. Okay? So if it's continuously compounding, after 5 years, you're going to make $382.36, which is a pretty decent amount of interest rate. Okay? Which means if you have credit cards, holy cow, because if you don't pay it off, you're paying interest on top of your interest, which is why you can never get out of credit card debt. Which is why continuously compounded interest can really, really be hurtful when you have a loan. Most credit card loans are continuously compounded interest. Simple loans like house loans or car loans are not, which is why credit card debt can be so dangerous because the interest continually, you're paying interest on top of your principal and your interest every day, which really can compound pretty quickly.